Alright, so today we start talking about the next chapter. We learned about the electricity, started with the static charge. Then we talked about what are the properties of the static charge. There are two kinds of charges. Like charges repel each other, unlike charges attract each other. Charge have an electric field around it, which you can feel the effect of the electric field by bringing another test charge around that. This electric field is responsible for the electric force, which we call F is equal to Q times E. We learned about the potential due to these charges. We learned about the conservation of the charges. Then we talked about the moving charge in the form of the electric current. Moving all over that, talking about the electric currents. Then we started talking about the magnets. We learned the magnets are of two kinds. The north pole, the two sides of the magnet, two poles of the magnet, just like the two kinds of charges, positive and negative charges. We have a north pole of a magnet and a south pole of a magnet. Magnets have the magnetic field around it, the vicinity, the region around the magnetic pole is called the magnetic field. Just like electric field, the vicinity, the region around the charge is called the electric field. Now the real question was whether we can have the electric charges and the magnetic field, they are somehow interconnected, and we learned, yes, that the moving charge is responsible for producing some kind of magnetic field. Alright. When I set a charge moving inside an external magnetic field, I learned about the magnetic force. First I learned about the electric force, then I learned about the magnetic force. Electric force is due to the static charge. There is the vicinity, the area, the region around it, there is electric field. And you can feel the force, the effect of that field. When I set the moving charge, there is a magnetic field. And we learned that the current carrying wire has a magnetic field around it. Now let's combine all this in the form of an electromagnetic induction to have more fun. So, for all these things, we know about the microphones, we know about the vending machines. Whenever we are hungry, we go to the vending machine to get the whatever is available and whatever we like it. By just swiping the card or throwing the coin into this vending machine, you get whatever you want to get by pressing this particular number. We also have, in the medical field, electrical stimulation of the brain that helps to treat the certain disease in the brain. How all these things work? How the vending machine knows that you put a quarter or a 25 cents or another dime or whatever, and that machine gives you whatever you're looking for, right? Your favorite stuff. All these things we will learn here in the electromagnetic induction. So in the case of the electromagnetic induction, few things we want to know, that we want to make sure that we know about the direction of the magnetic field produced by an electric current. Recall yourself that the current carrying wire, I grasp the wire in such a way the thumb points in the direction of the current and my fingers curled around this wire will tell me the direction of the magnetic field around it. At every point the direction is changing. It's just like a circle, and you have a circle and the tangent to the circle. So as I keep curling my fingers, the direction of the magnetic field is changing depending on which side I'm looking at around the current carrying wire. If you haven't, please look at the previous chapter and remind yourself we talked about that. Now, we also learned that how to find the direction of the magnetic force exerted on a moving electric charge when it is placed in an external magnetic field. Alright? We said we can use, for the positive charge, we use the right hand, the fingers pointing in the direction, along the direction of the magnetic field, thumb pointing in the direction of the motion of the charge, and the line which is coming out of the palm or perpendicular to the surface of the palm, that is the magnetic force. We learned that the electric field produces a current in the wire, and how the current relates to the resistance of the wire, we learned that in chapter number 19. So all these things will be used over here. Now, what is new in this chapter? We talked about the current, electric charges, electric current. We talked about the magnets and the magnetic field. What is new here? We learned the electric current through a wire produces a magnetic field. We said the moving charge produces a magnetic field, which that magnetic field we can find out by grasping the wire in our hand in such a way that we're talking about the conventional current again. So thumb points in the direction of the current and the curled fingers tell you the magnetic field. So if the magnetic field is there, you can see it through a compass needle. By placing the compass needle close to the current carrying wire, you will find it that the direction of the magnetic field at every point around it. That's all good. Now the thing is, we want to see, this was that the moving charge can produce an electric current, and a moving charge can produce a magnetic field. But now, whether the reverse is also possible, what is the reverse? That it could a magnetic field, moving magnetic field can also produce an electric current. That is a beautiful phenomenon. It took several years for the scientists to answer this question, because this was very important to know that if the moving charge produces a magnetic field around it, so if I change the magnetic field, can I produce an electric current? So in this chapter, this is exactly what we are going to investigate. Under what conditions we can do that? We can produce the electric current by the moving magnetic, by the changing the magnetic field. Now, this is called induced electric current. we learned that the electric current is produced. Electric current is a result of a battery connected to an electrical circuit and the switch is on or switch is closed. So when the battery is connected to a circuit or to some device, the current and the circuit is closed loop, the current flows through the circuit. And there, when the current flows through it, there is an electric field there, right? Now, in electromagnetic induction, the induced electric current, we will learn that how I can produce an electric current without a battery. Earlier we learned the electric current is there because we connect the battery, the power source. Here we want to see that how can I produce the electric current without a power source. And that electric current is called the induced current. You use your cards, credit cards or debit cards into the machine, so you get the money from there, right? If you have the money in your bank account. You can also turn on the lights with the electromagnetic induction. It's a beautiful phenomenon. These are the few things, the few sources. The magnetic fields are produced by the few examples the magnetic field is produced by. A current in a current carrying wire has a magnetic field around it using this right hand, depending on the conventional current orbits. If I turn this straight wire into a loop, then it's a loop of wires using the same procedure I will see in the middle of the loop. It looks like I have a magnet placed in it. One end of this magnet has a north pole, the other has a south pole, so the magnetic field lines move around it. Now, instead of one loop of a wire, if I connect several loops of a wire, we call this solenoid, a fancy name. So that means we have a strong magnetic field around it. Then we also have a bar magnet, the magnetic field around it. And then the earth also is a source of the magnetic field, right? We learned that the earth has the center of the earth behaves like there is a giant magnet in there, okay, due to some phenomena. Sun is a source of the magnetic field. Now, here is an experiment. In this experiment, we hold a magnet which is motionless in front of a current, in front of a coil, current conducting coil. And then there is a galvanometer which shows you the deflection in the galvanometer will tell me that if there is a current flowing through this. So I have this current carrying coil and a galvanometer. The needle of the galvanometer is in the middle, which is showing you 0. Alright, now if I bring a magnet close to that, and you will see if something happens when I bring it, you see there is a motion in the needle, but then other than that I hold the magnet still, it's not moving, it's nothing going to change. No motion in the needle of the galvanometer. Alrighty? So no current produced. No matter whichever side, as long as it is still, it's not going to change anything. Now, it's been noticed that on the other hand, if I take this coil with the galvanometer, and now instead of being still magnet, you will see if I change the magnet, move the magnet, the needle of the galvanometer moves, right? Depending on if I bring magnet closer to that or take it away, right? So something is there. The current is produced when I move the magnets, right? So a current is registered in the coil without a presence of a battery. The current is flowing through it, and the galvanometer shows, the needle shows a deflection, right, towards right or left depending on the direction of the current changes. So that is, we move the magnet either close to it or away from the coil, and you see the deflection in the needle. If I am going towards it with the north pole into the coil, you see the deflection towards positive side, and if I take it away, move away from it with the north pole moving away, you have negative side. And if you put the south pole, that will also be in one side or the other. Now, for the current to exist in any conducting coil or in any conducting wire, there got to be a source, the power source, which we give the fancy name called electromotive force or source of EMF. There got to be a source of EMF. Alright? Now, instead of moving the magnet inward or outward, let me rotate the magnet and then see the fun. The current is still registered as I rotate the magnet. Instead of moving backward or forward, I just do this. So here I see, so instead of doing this, I rotate the magnet, and you still see the current is registered in the deflection, in the form of the deflection of the galvanometer's needle. Alrighty? There's another way to look at that. If I put this magnet here and then I move my coil either towards it, the magnet, or away from the magnet, the current is registered in the galvanometer in the form of the deflection in the needle. Okay? So something is there which produces the EMF. Okay? So what produces the EMF in these experiments? Although we do not use any battery, the electric current is induced in the coil when either you move the magnet close to the coil or moving the magnet towards the coil or away from the coil, or you move the coil close to the magnet or away from the magnet. In either case, or you rotate the magnet close to the coil, the current is registered. It means there is a change in the magnetic field which is responsible for producing the current. Alright? Here is another way to look at it. What is happening? Now remember, we said we can use the left hand for the negative charge and right hand for the positive charge. Same thing we can do it here. Okay? So what I'm going to do, if you look at this, at the top and the bottom sections of the loop, we see a component of the magnetic field which is perpendicular to the velocity of the loop. What is the velocity of the loop? Is mean I have a magnet and I'm bringing the loop closer to the magnet, right? So that is the velocity of the loop. Whereas the magnetic field lines go from north, alright, So at the edges, you see the magnetic field is going like this, in between horizontal and vertical components. Now I want to see with this magnetic field, the vertical component of the magnetic field is here, velocity component is here, the motion of the charge, because the conductor has the charges in it. So when I move the conductor, it means I'm moving the charges in it, right? So I take the perpendicular component, because if I take the parallel component of the magnetic field, which is in velocity vector and the magnetic field, they are in the same, along the same line, so there is not going to be force, okay? Only the vertical component of the magnetic field. So if I do that, look at this. This is the magnetic field vector, okay? And this is the moving charge, like this. This is a negative charge. I'm going to use the left hand. So my fingers pointing in the direction of the magnetic field, and then my thumb pointing in the direction of the motion of the loop, which means the charge is moving that way, because I move the loop, loop carries the free charges, okay, conducting loop. Now what will be the direction of the magnetic force? That will be perpendicular to this. It means the force is going to be into the page. Now the same thing when I look at this. So the magnetic field is down, the moving charge is this way, so the force is outward. So here the force is outward, here the force is inward. Alright? So all I did is, I have the magnet placed somewhere and the loop is moving towards it, and which means as a result the charges, the free conducting charges inside the loop, they move, and by using your left hand for the negative charge, electrons, free electrons are always available, okay, in the conductors. So you see the component of the magnetic field and the velocity of the charged particle, they're perpendicular, and the force is produced in the alright. So in this case the force is in the one direction, in this case the force is in the opposite direction. If you look at it, so basically the electrons moving, accelerating the electrons, this force is responsible for moving the charges, and the current is produced. Our friend Newton says F is equal to ma. Whenever a force applied on a mass m, an acceleration is produced, it means this electron is accelerated, this electron is accelerated, okay, with the magnetic force. So the current, the charges are moving in a clockwise direction. Current is produced. That is what we registered. Alright. So inducing the magnetic field, we learn how we can do that. I can simply take a conducting loop and move close to the magnet, or away from the magnet, I can induce the current. Or I can move the magnet towards the coil, or away from the coil, I can induce the magnetic electric current into the in the conducting coil. All right. How many it all depends how much magnetic field lines pass through the conducting coil. The strength of the electric induced EMF will depend on the number of magnetic field lines passing through the coil. Okay. More the magnetic field lines, more the induced current. More the magnetic field lines changing through the coil, more the magnetic induced current produced. Right? If the magnetic field lines increasing on one side, the induced current will go in one side, and then if you take the magnetic field lines away from it, so magnetic field strength is decreasing or increasing, the current will be moving in depending on the direction. So what we did two different experiments. In the one experiment, we said the induced current is caused by the magnetic force exerted by the moving electrically charged object. That's what we learned in the previous chapter. Sorry, no, the induced current we said is caused by the magnetic force, right, exerted on a moving electrical charged object. Previously we saw that. Then we said in explanation 2 that any process that changes the number of magnetic field lines through the coil area induces a current in the coil. This mechanism explains how it happens is unclear totally at this point. Okay? In the first explanation, the induced current is caused by the magnetic force, okay, exerted on a moving electrically charged object here. Okay? In the second case, we are saying that any process that changes the number of field lines, like this, you are bringing the magnet close to the coil or taking away from the coil. So the field lines are changing through the cross-section area of the coil, and that will correspond to EMF produced in the coil. And this will lead to this EMF will lead to the induced current. Now here is another way to look at it. Let's put the magnets away. Let's take the two coils. One coil is just connected to a galvanometer and not any power source, whereas the other coil is connected to the power source as a battery, and the switch is open. So when I place these coils close to each other while the switch is open, so basically both coils have no current flowing through that, so nothing is going to happen. They will keep staying there forever. Now let's close the switch. As I close the switch, all of a sudden, the moment I close the switch, the charge starts flowing and the current increases. As the current increases through the coil, the magnetic field is produced around this coil, and those magnetic field lines increasing through the other second coil, which is connected to the galvanometer, and you see the current is induced in that second coil, the top coil. Okay? But that is what happened when I turn on the switch or close the switch. Alright? Now, we keep the switch in the circuit for the coil 1 closed. Now the current, first I turn on the switch, the current will start increasing in the first coil, and then as a result the magnetic field lines induced, they will keep increasing and the current is induced. Now let's see, if I keep the switch on and after some time there will be a steady current flowing through the coil. It means the magnetic field lines are no more changing. Magnetic field is produced, that is steady current, no more change in the current, no more magnetic field lines are changing anymore. So the second coil will not show you any more induced current, because this stable current has been flowing through this coil 1. Magnetic field lines which were induced in the beginning, they are not being changing anymore, so no more current in the second coil. Okay? So that tells me something, that there is some phenomenon going on which has related to the change in the magnetic field. Now let's turn off the switch. When I turn off the switch, then you see the current in the first coil will start decreasing, which means as a result the magnetic field induced by this current in the first coil will start decreasing. As a result, in the second coil you will again see the induced EMF and the current. So it means there is something to do with the change in the magnetic field. It's just not the magnet bringing closer to it, but changing the magnetic field lines passing through a certain cross-section area that produces the electric current. Okay? Now that is called electromagnetic induction. So which means it is possible to have the current in a closed loop wire without using a battery. This phenomena of having a current in a closed loop wire without having a battery is called the inducing the current using a process of changing the magnetic field, and this is called electromagnetic induction. All right. Induction means we induce the current by changing the magnetic field lines through the cross-sectional area of the wire, crossing area of the wire. See, the same phenomena takes place here. I have a magnet placed on this stand. This magnet is fixed. Now what I have here is a conducting coil which is attached with a block, and the block is attached with the spring and is hanging up there. Now if this block has a weight, it will come down due to the gravity, so it means the coil will come towards the magnet and the magnetic field lines are going from the north, so it means the crossing of the magnetic field line through the coil will change. The magnetic field line through the cross-section area of the coil will change. As a result, the current will be induced. It will be registered into the coil. This phenomena is used in the microphones and the speakers as well, of course. How? Here it is. This is the fancy looking microphone. All it has is a conducting coil, right, on a diaphragm which will be vibrating, and then there is a magnet over here at the end. Now when I speak, this process of speaking, my sound waves from by motion of my lips, the air particle closer to my mouth, they will be compressed and then they will be decompressed. Compressed and decompressed with the motion of my lips. So the sound is producing this vibration in the air particle. Those air particles go into the microphone, right? You see the microphone has this the shape. It looks like the air particle can enter into it. Now this will vibrate this diaphragm back and forth. As a result, this has a conducting coil on it. As a result, the magnetic field will change through this diaphragm and the current will be induced. How fast you speak depending on the pressure of your waves, sound waves, that will induce the current, and then this electrical signal will go to the amplifier because the microphone is attached to the amplifier. The amplifier will enhance the signal, and then this electrical signal go to the loudspeaker. Over there, this reverse phenomena, the same phenomena takes place. The electrical energy will be converted to the sound energy back again through the speaker, diaphragm of the speaker. Alright, with the vibration on the speaker will take place, and that will vibrate the air particle next to it, and then you will hear the music, whatever you want to give. Alright. Now let's put all this together. The Passing of the magnetic field lines through the cross-sectional area is called the magnetic flux. A physical quantity that measures the number of magnetic field lines passing through a coil's area. In other words, I can say that the magnetic flux is proportional to the strength of the magnetic field lines passing through the plane of the loop of the coil or the area of the coil. Alright? For example, here I have a coil and the magnetic field lines are passing through it. So now the magnetic field lines and the area vector to the coil are in the same direction, they are making same angle theta. So here it is. So this is a coil. The magnetic field lines are going through this, alright, and the area vector is a vector perpendicular to this area of the cross section of the coil. That area vector, okay, the normal, the perpendicular to the area vector and the magnetic field lines are in the same direction. So the angle between them is 0. As a result, so the field lines are passing through it. Now, on the other hand, if I place the coil like this, the area vector is now perpendicular to the magnetic field lines, which is making an angle of 90 degrees. Now, here in the third scenario, there is some angle between 0 and 90 degrees. Between the area vector of the coil and the magnetic field lines. Now, put this all together in the mathematical form, and we call this a magnetic flux. It's represented with the letter phi, the Greek letter phi, okay, and subscript B over here for the magnetic flux. B dot A. And if you remember, in the case of the work, we said F dot A, D, and B dot A is B times A cosine of the angle theta. A is the area vector, this is a vector, okay, as you see in the boldface. But now it's not a vector anymore. Okay, theta is the angle between the magnetic field B and the normal to the plane area vector. This, okay, normal to the plane area vector. Now the standard unit for this flux is Weber, and Weber is Tesla times meter squared. Now the flux is max when the area vector and the magnetic field lines are parallel to each other. See, the coil is placed perpendicular to the magnetic field line so that maximum lines can pass through it. So area vector to the plane of the coil is parallel to the magnetic field. So the cosine of the angle theta is 0, cosine of 0 is 1. So if theta is 0, cosine is 1, and then maximum magnetic flux. So now here you can see the magnetic field lines. So this is the side view of the coil. So the area vector and the field lines are perpendicular to each other. The area vector and the field lines are parallel to each other, and this is along the area vector is along the direction of the magnetic field line, so the theta is 0. On the other hand, if I rotate this coil, now my area vector, when I rotate it, the area vector is on this side if I am looking at through this side, okay? So if I just look on one side of this coil and just keep this side and I rotate it, now the area vector on this, now the theta between them is 0, right? 180 degree. Now in this case, when I put it along the plane, along the magnetic field lines, so theta is 90 degree between the magnetic field lines and the area vector. So here the flux is 0, here the flux is negative B times A, here the flux is B times A max, and here the flux is B times A times some angle, whatever this angle is, cosine of theta. So if I keep rotating this coil, so that I keep changing the flux, so it means I am keep inducing the current. Alright, here is an example. A circular loop with a diameter d is in a uniform magnetic field B and an angle theta is shown in the figure. So what is the magnetic flux through the loop where the magnetic field is 0.23 Tesla and distance with diameter of the coil is 15 centimeter, and it makes an angle theta. Okay, the coil makes an angle theta with the magnetic field line. So the area vector to the coil is, this is the area vector. Okay, now if this coil makes an angle theta, so what is this angle between the magnetic field line and the area vector? Okay, so this whole thing will be, this is pi by 2, alright, this is pi by 2 and this is pi by 2 minus 30. So that will be the cosine of the angle. So which means A dot B or B dot A is equal to cosine of this angle pi by 2 minus theta. And cosine of pi by 2 minus theta is equal to sine of theta. Okay, trigonometric identity. Okay, which is basically cosine pi by 2 cosine theta minus, which will become plus sine pi by 2 sine theta. Alrighty. So this will, cosine pi by 2 is 0, so it means this whole term is 0. This will be sine pi by 2 is 1. This will become sine theta. That's what you have. So you plug that in over there and you get the, okay, plug in those numbers, you get the B dot, A dot B, this is A dot B. Okay? Get the flux. Alright, so we learned several things, that how can I induce the magnetic flux and induce the EMF. So it means if I turn this switch on, open switch does not do anything. The two coils, okay, one is connected to the power source, other is not, but connected to the galvanometer. The moment I close the switch or open the switch, the current will increase or decrease, and magnetic field lines due to the current will be induced, increase or decrease through this coil. Changing magnetic field will produce an electric current. Here, if I move the magnet close to the coil or away from the coil, you will see the induced current and the moving magnetic field. Here, instead of moving the magnet, I move the coil in between the magnetic field line or away from the magnetic field line. In either case, the magnetic flux is changing and the induced EMF is there.